All right, let's get started. So yesterday we introduced Newton's three laws of motion. And what our goal is today is to learn how to use those three laws of motion to figure stuff out. We're going to learn how to solve problems in a Newton's law context. Now, what you're going to find is that solving problems in chapters 4 and 5 and even 6 is really, at the end of the day, not any different from solving any other physics problem. Uh, so, in a lot of ways, the process that you'll use to solve problems using Newton's laws is the same process you've been using since chapters 2 and 3. What's going to be different is the way that you will implement that process. So, just to sort of make sure that we're all on the same page. Back in chapter 2, every time we did a problem, I always suggested that step 1 would be to draw a diagram, right? Always draw a diagram. And the reason that you're doing that is because physics is not a math class where you just have numbers and equations without any context. You're always describing some kind of real world situation. And a big part of learning physics is learning how to take that block of text and translate that into something workable and think through the way things are interconnected. And the diagram is going to help you sort your thinking out. So don't skip that. Start with a diagram. It's going to help you sort of keep track of stuff. And you're going to find this is going to work in chapter 4 as well. We're going to start with a diagram. It's just going to be a different kind of diagram. The second step of every problem back in chapters 2 and 3 was that once we had a diagram, we ended up choosing a coordinate system. And take inventory. So that's going to be equally important this chapter as well. We're going to always end up choosing a coordinate system, and we're going to take inventory of what information we have. But again, the way we implement that step is going to look a little different in chapter 4. We're going to be taking inventory of different things in a different way, but it's the same basic process. All right. In chapter 2, the third step was always to find some equations that related what you knew to what you needed to know. And we're going to do the same thing in this chapter as well. We're going to find some equations. Now, what's different is that back in chapter 2, the equations that we were using were almost always going to be the same 4 equations of motion, right? The position equation, stop velocity equation, what I call the stopping distance equation, and the useless equation. And you were almost always picking one of those 4, and you were choosing based on which ones included whatever you were trying to solve for, but avoided stuff you didn't know. In this chapter, what's going to happen is the equations that you're going to end up finding aren't going to come from some predetermined list. You're not going to memorize those equations, but instead, you're going to learn how to build them for your particular scenario based on whatever you had in the previous step. So you're still finding equations. You're just going to generate them yourselves rather than memorize them. And then step 4 is still going to be to solve that puppy, right? Once you've got a bunch of equations, it turns into a math problem. All the physics happened up here. Once you get down to here, you've got some equations. You just solve those equations, which means doing some math, right? So this process is going to be the same for literally every physics problem ever. It's just the way we implement those 4 steps is going to look a little different depending on what context we're operating in. So we're going to learn how to implement these sorts of steps for a Newton's law problem. So let's start with that diagram, right? Back in chapter 2, every time you drew a diagram, you were dealing with kinematics. And in kinematics, you care about keeping straight where things are, how fast they're moving, what their accelerations are. And so your diagram tended to be about, labeling where the object was at this time, where the object is at a later time. And keeping track of positions and that kind of stuff. But in a Newton's law problem, what we're going to care about are forces, right? The thing we're going to be paying most attention to is not who is going where or who is traveling with what velocity, but rather what objects are pulling in which directions and how hard are they pulling. And so the kind of diagram that we're going to use in this chapter is something called a free body diagram. Right. A free body diagram is going to be a simplified sketch of whatever it is that's happening in your situation. But what you're going to do is you're going to take whatever your object of interest is, and you're going to label all the forces that are acting on that object. And forces are vectors, right? So you're going to draw them in as little arrows that point in the appropriate direction. And that's our goal in a free body diagram, is just to figure out what are all the different pushes and pulls that are acting on whatever object is we're trying to figure stuff out for. So imagine that I had something simple like a book resting on the ground. Here's my book, here's the ground, and I want to think about what forces are acting on that book. And once I've identified a force, I'll just draw an arrow representing that force and label it appropriately. Now, what are the forces acting on that book? Well, obviously gravity pulls on the book. And we learned about the force of gravity yesterday. The force of gravity is also called the weight. And obviously the weight of the object is gravity pulling the object downward. So I'll draw an arrow pointing downward, and I'll label that maybe with a W for weight. And of course, I know the weight is m times the acceleration of gravity. So maybe I'll even note that it's m times g. That's how we find the force from gravity, because obviously that's one force acting on the object. Yay. Now, we also know from Newton's second law that the sum of the forces is equal to the mass of the object times the acceleration of the object. But we're talking about a book sitting on a table. That book is not moving at all, which means it can't be accelerating at all. And if that's the case, if it's not accelerating, that means there can't be a net force. If gravity's pulling this thing downward, the only way this thing shouldn't be falling downward is if something else is pushing it upward. And so there's got to be a force being exerted by the table, right? The table is touching the book, so it's pushing it upward. And I can name these forces whatever the heck I want. We'll come up with specialized names for things later, but the names of stuff in physics are not especially important. Right now, I'm just going to call it, the table. Right? We'll worry about names later. But clearly, excuse me, there's got to be some upward force. Otherwise, it would be falling through the table. The table's pushing it up to prevent it from falling. So for this simplest of all possible problems, there is my free body diagram. Now, most forces are forces of contact. And right now, there's nothing else touching my book. So there should not be any other forces. Good grief. I'm allergic to the state of North Carolina. Thank you. All right. So bottom line is, there's my diagram. It's labeling all the forces that are acting on my object. That's step one. If you had multiple objects, you might choose to do multiple diagrams. So for instance, if I had, here's a guy pushing his lawnmower, right? Well, maybe for this problem, maybe I care about the forces being exerted not just on the lawnmower, but also on the guy. I might choose to do my free body diagram where I separate the two objects so I can be super clear what forces are what. So for instance, if I'm doing just the lawnmower, I might draw that off to the side. And what forces are acting on the lawnmower? Well, gravity pulls the lawnmower down, right? but the lawnmower is touching the ground. The ground is going to push the object upward. So I've got a force from the ground pushing it upward. Now, what else is touching the lawnmower? The guy is touching the lawnmower. The guy is pushing the lawnmower forward. I'm sorry?
I need clarity. I know it's like why that thing is pushed down because of gravity. What's pulling him up?
The ground. The ground is touching it. And if not for the ground, it will be falling. So the ground must be pushing it upward. It seemed, if that seems weird to you, it's because you're not used to the idea of there being forces from like inanimate objects. You don't think of the ground as being something that pushes you. But try this. Stand up.
Okay, I am.
Right. What do you feel right now? What's pushing you at this exact moment? What do you feel right now?
Nothing.
Are you sure?
I'm just standing.
Uh-huh.
I guess the floor is like pushing you up, like you're standing, like
yeah,
you know,
like if I know that when I'm teaching like in a class on all my feet for like 8 hours a day, a lot of times at the end of the day my feet will be sore. Why are my feet sore? Because all day long the ground is pushing up against my feet, right? So yeah, the ground is pushing against you. You don't notice it, but it's certainly there. You know, if you jump and you hit the ground, you're going to feel the ground pushing up against you to stop you from falling, right? The ground exerts a force on you all the time.
Okay.
That force is bigger if you jump up and down, but it's always there.
Okay, got it.
Yeah. So, yeah, there's a force of the ground pushing it up. Now, what else is touching it? The dude. The dude is touching it, and he's probably pushing the lawnmower forward. So maybe I'll call this P for push. That's the force of the guy pushing it forward, right? Oh, but the lawnmower is maybe dragging across the ground. Maybe there's a frictional force that tries to slow it down. So maybe that force is the friction. And you'll notice each of those forces is in a different direction. The guy pushing it's trying to make the thing go forward. The friction is trying to slow the thing back down. Gravity's trying to make the thing fall. The ground is trying to keep the thing from falling. So those are the four forces that are acting on the lawnmower. But what about the guy? So off to the side, I might draw the guy separately and ask myself, what forces are being exerted on the guy? Well, gravity pulls the guy down, so there's gravity. Right, pulling him downward. The ground is going to push him as well. Now, the ground is going to push him with a different amount of force than the ground pushes the lawnmower because this guy's probably heavier than the lawnmower. So maybe I'll call this ground 1 and this ground 2 because they don't have to be the same size force. But what does have to be the same is if this guy is pushing the lawnmower forward, if this P is the force of him pushing the lawnmower, Newton's third law says that the lawnmower pushes back against the person with exactly the same force, but in the exact opposite direction. Does that make sense?
No, can you say that part one more time?
So if he's pushing the lawnmower forward, right? Newton's third law says that for every force on an object, there's an equal but opposite force on another object. If I push you forward, you are in fact pushing against me the exact same amount of force in the opposite direction. So if this is the guy pushing the lawnmower forward, the lawnmower is pushing the guy backwards.
Okay.
Now, what's happening is, why is he not flying backwards? Well, because his feet are sliding against the ground. There's a force of friction from the ground. I'll call that friction 2 because it's not the same as friction 1. This is what's propelling the guy forward. That's why, like, if his shoes were super slippery, he wouldn't be able to push forward because he couldn't get traction. So this is the traction of his feet pushing him forward.
Okay.
And you'll notice I've got, free body diagrams for each object. I've just labeled all their forces. There may be some forces in common and other forces that are unique to each diagram. So every problem that we do is going to start by doing one or more free body diagrams just to keep track of all the different forces that are acting in the problem. And the first thing you're going to have to learn how to do is identify what forces you've got. Now, one thing that I find will often make your life easier is when you're doing these free body diagrams, you think about it in terms of objects, because for every force, there's got to be a pusher and a pushee, someone doing the pushing and someone getting pushed. And the only force that we're going to talk about all semester long where the pusher and the pushee don't have to be touching is the force of gravity. For every other force, the pusher and the pushee have to be in physical contact. And that will hold true for pretty much this entire semester. Next semester, we'll learn about some additional forces that are also field forces like gravity, like magnets. Magnets don't have to touch each other to pull. We'll learn about them next semester, but that's for a later discussion. So like when I was thinking about the forces on the guy, all these forces had to be from something touching the guy. This was because the guy was touching the lawnmower. This is because the guy is touching the ground. This is because the guy is touching the ground. So those are all things that are in contact with him, but there's nothing else touching him, so there can't be any additional forces, right? The only thing touching this lawnmower is the guy and the ground, so the only forces I have are from the guy or the ground. Does that make sense?
Yeah.
What's that? Okay. So that's going to be our next step is doing this free body diagram. And then what's going to happen is we're going to choose our coordinate system and take inventory of what we know, right? And back in chapter 2, taking inventory meant, finding the starting position, ending position, starting velocity, ending velocity, acceleration, and time, right? 6 things. Here, what's going to happen is taking our inventory is going to be more about keeping track of the direction and the vector components of all the things in this free body diagram. Let's, I don't want to do this problem in its fullness because that's more complicated than I want. Let's go with something still a little simple, but not ridiculous. Let's imagine I've got a box sitting on a slippery ground. I'm going to say that it's slippery so that there's no friction. And I tell you that the box has a mass of 10 kilograms. And I'm going to push it with sideways, or heck, let's do better. Let's push it diagonally with a force of 100 newtons. So I'm going to pull with a force P, and P is going to be equal to 100 newtons. And I'm going to drag it like that at an angle of 30 degrees with respect to the horizontal. And what I want to do is to take inventory of what I know. So I start with my free body diagram. I've got me pulling it diagonally. There's gravity pulling it downward. There's the ground pushing it upward. We're going to give that a name, right? And again, I don't want you to get you too hung up on names, but we're going to call this N for the normal force. Now, what is that even about? It's super easy. The word normal is a math term, and it just means perpendicular. Right? That's what the term means. And so oftentimes in physics, you'll have situations where two objects are touching each other, and there'll be a force of contact between the two things. But what's going to happen is that force of contact is typically going to be perpendicular to the surface. For instance, if I have an object sitting on the ground, Well, if the ground is horizontal, the force from the ground will be perpendicular to the ground, which in this case would be straight up. So that's why this normal force points straight up. But what if the surface were not perpendicular? What if I were to turn around and press against this green screen behind me? Now, I'm pushing this way. That means the wall is pushing me towards the camera, right? Because the wall is vertical, the normal force from the wall would be horizontal. Does that make sense? So if I was pushing up against a horizontal wall, the normal force would be just perpendicular to the wall. What if I was on a slant? Here's slanty ground. I put a box on the slanty ground. Well, what's going to happen is the force from the ground would not be straight up anymore. It would be perpendicular to the ground. So the normal force might be a little bit slanty if I was on an incline. What if I was on a curvy surface? I've got a box sitting on a round hill. How do you find the perpendicular to a curvy surface? Well, if I was over here, what I would do is I would take a tangent line, and I would draw the force from the ground being perpendicular to that tangent line. So there it would point like that. At the top of the hill, the normal force would point straight up. But over here where this guy is, the normal force is going to point slanty that way. So on a curved surface, the direction of the normal force can be different depending on where on the surface you are. So that's a term that we'll throw around a lot. But, you know, if it gets confusing, just remember, what I'm calling N for the normal force is really just the force from the ground. That's what it is. So far, so good?
Yep.
So I've got these three forces acting on my object. And what I want to do is choose a coordinate system and break those forces down into their components the same way we did back in chapter 3. So when I take inventory, what I'm doing is I'm looking at that picture and just breaking them down into their requisite bits. So for this, let's go with a regular boring coordinate system. Let's have sideways be the x direction. Let's have up and down be the y direction. I'm going to have positive for x be to the right. I'm going to have positive for y be upward. So I'm just making that choice. Maybe the box starts at 0, 0, but since I'm not worried about where it's going, I don't care about the 0 point quite so much. So that's my coordinate system. Now, when I'm looking at these three forces, what's going to happen is the normal force is a vector, and it's going to have some magnitude. I don't know how big that normal force is. I'm just going to call that n, and n is a number that I could solve for. But I do know that whatever the heck n is, it points straight up. It points in the y direction, but it doesn't point sideways at all. So I could say that it's going to equal 0 I hat, because remember, I hat is the sideways direction. But it's whatever the heck n is, j hat. So I've taken inventory of that by breaking it into its requisite components. What about the weight? Well, the weight is the force of gravity. I'll call that W. It's a vector. Now, the weight has a magnitude of m times g, but it points downward. So it's not sideways at all. It's going to be 0 in the x direction. But in the y direction, it's going to be mg, and since it's downward, I'm going to slap a minus sign on it. So it'll be that in the j hat direction. So far, so good? Now, what about that push? Well, that push is tricky because it's diagonal. And because it's diagonal, it's going to be a little bit sideways, but also a little bit up and down. And so when I do its components, unlike the previous two that were 0 in one direction and something non-zero in the other direction, this diagonal push force is going to be a little bit in each of the two directions. And how do I find out how much of it is in each direction? I use SOHCAHTOA. Right, P is diagonal. It has a length of 100 newtons. There's the X component. There's the Y component. And this angle was given by the problem to be 30 degrees. And so to figure out the X component, what I would do is use the cosine. I know that the cosine of 30 degrees should be the adjacent side, which is whatever the X component is, divided by the hypotenuse, which is 100, or let's just call it P, where P is equal to 100. I'll plug the numbers in later. So if I wanted to know what the X part is, I just multiply both sides by P. So P times the cosine of 30 is equal to the X part. So when I do P as a vector, it's going to be whatever P is times the cosine of 30, and that's the I hat part. It's to the right, so I'm going to leave it positive. And then for the Y part, I do the same idea, except now it's the sine. I know the sine of 30 is opposite, that's the Y part, over the hypotenuse, which is P. So again, when I rearrange that, I get that the Y is equal to P times the sine of 30. It's upward, so I'll leave that positive. So what I have done is I've taken my free body diagram, and for every force that appears in the diagram, I've broken it up into its requisite components. That's how I'll take inventory in this context, right? I'll figure out how much of that my force is in the X direction, how much of the force is in the Y direction, and break it down accordingly. Neat. So what's my third step? My third step is find some equations. And what's going to happen is in this chapter, you're not going to have a list of equations to memorize. You got one equation you need to know. It's the same equation every single Newton's law problem, right? And that equation is Newton's second law. What is Newton's second law?
F equals mass times acceleration.
Yeah. Newton's second law says the sum of the forces, and that's important. The F in F equals ma is not just one force, it's the sum of all the forces equals ma. Now, what's going to happen is when I break that down, sum of the forces equals ma. The thing that I have to remember is that F is a vector, A is a vector. So both of these things are vectors. And so when I say I'm adding up all the forces, I have to add up all the forces, but I have to do them like a vector. And remember what happens when you add vectors? You add the X parts to the X parts and the Y parts to the Y parts separately. And what that means is even though I'm writing like 3 letters here, F equals ma, really what I'm saying is that to do the sum of the forces, I got to take all the forces in the X direction and add them up. So all these forces added up is going to equal the mass of the object times whatever acceleration I've got, but it'll only be the X part of the acceleration. The acceleration might be a little bit sideways and a little bit up and down. It will have components as well, just like this did. And so the equation that I'm going to get are going to be one equation for the X direction and a second equation for the Y direction. And all I've got to do is apply this idea to this inventory, and I'm good as gold. So what's that going to look like? Well, let's do this example problem. I'm trying to give enough space where you can see it all on camera here. There we go. So I want to do the sum of the forces in the X direction first. Well, in the X direction, I have 0 for the normal force. I have 0 for the weight, but I do have the push times the cosine of 30. That's the only force in the x or I hat direction. So the left-hand side of this equation is going to be just P times the cosine of 30. Boom, full stop, I'm done. That's got to equal the mass times just the x portion of the acceleration. So I'll call that a sub x. It's whatever acceleration my box has in the sideways direction. But what about in the y direction? Right? I'll go back. In the y direction, I have many forces. So what's going to happen is in the y direction, I'm going to have this force, N, plus this force, so negative mg, plus this force. And that's going to have to equal the mass of my object times whatever acceleration my object has in the y direction. So when I go to generate my equations, right, all I've got to do is that. There's my equations. Yay, super awesome. And from there on out, once you've got your equations, this is going to turn into a math problem, right? You just solve it. Now, when I'm looking at this, in this upper part of the equation, which of these things do I know? Well, I know that the size of the push was 100 newtons, so P was given. Cosine of 30 is just a number, so I got that. The mass was given to be 10 kilograms, so I've got that. And the only thing in that equation that I don't already know is the acceleration. So I could totally just find the acceleration. So the sideways part of the acceleration, I'll just get by dividing that. So A will equal P cosine 30 divided by M. That's 100 times the cosine of 30 degrees divided by 10. And the cosine of 30 is going to be square root of 3 over 2, which is about 0.866, times 100 is 86.6, divided by 10 is 8.66 meters per second squared. Piece of cake. So we now know how much it's going to try to accelerate sideways. Now, what about up and down? Is there a up and down component to its acceleration? Well, here's where maybe you have to do a little bit of common sense. So if I'm looking here, this was given, this was given, this was given, this was given. Everything in this is known except for the normal force and the acceleration. And that means I have two things in this question that I don't already know. However, let's think this through. I've got N minus M, that's 10 times 9.8 plus 100 times the sine of 30 equals the mass, which is still 10 times whatever the heck the acceleration is. Now, what's going to happen is the parts that I have numbers for, I can crunch those really quickly. So this is 98, and it's negative. And then this is 100 times the sine of 30. That's 50. So what's going to happen is I'm going to have negative 98 plus positive 50. All right. That's going to be negative 48. So I have N minus 48 equals M times AY. Now here's where I have to stop and do a little common sense. Now, what could have happened if this guy was pulling super hard? It could be that you're pulling hard enough to lift this guy up off the ground. And in that case, the normal force would go away because I would stop touching the ground. However, when I look at my actual numbers, what you see is that the force of you pulling up is only 50 newtons. The force of gravity pulling it down is 98 newtons. I'm not lifting hard enough. Even if I pulled straight up, I couldn't lift this guy up straight off the ground. So it's not going to rise up off the ground. However, by the same reasoning, by the same reasoning, it's not going to fall through the ground either, right? So what's going to happen is the force of the ground pushing up is going to prevent it from falling at all. So I expect from common sense that this object won't move up and down at all, and I can tell that the acceleration has to be 0. Now, someone was trying to interrupt me. What was the question?
I had a question.
Okay.
I know for the top part you put equals 10 AY, but when you brought it down, it went to MAY. I was asking how did that?
Oh, M was 10. I like to plug the numbers in at the last minute, and I just accidentally wrote M again, even though I'd already substituted in.
Oh, okay.
So I could have done 10 AY. It doesn't matter.
Okay.
Yeah. And notice here, since AY is going to be 0 anyway, it didn't make a difference. But yeah, I 10 and M, they're the same thing. So notice what's going to happen is if this thing's not going to fall through the floor, the only way that can happen is if the ground pushes up enough to cancel out that negative 48 Newton downward force. So that means the floor has to push up with 48 Newtons of force. So we were able to solve for that as well. So in this problem, given these inputs, this thing here is going to get dragged across the ground with an acceleration of 8.66 meters per second squared. It's going to keep speeding up by that amount every second. But it won't lift up off the ground because I'm not pulling hard enough in the vertical direction. So at the end of the day, those are my steps. Those are the steps that I'm going to use every single time, no matter how complicated the problem, no matter how many forces I have acting, no matter how many objects there are. Those are my steps for every single problem. And all that's ever going to change is the way in which I implement those steps. Sometimes there will be a trick that you'll have to employ as you're filling in some of these blanks to help you get where you're trying to go. For this particular problem, one of the tricks was realizing from common sense that this object could not fall through the floor because the floor is not going to let it. And that allowed me to make the assumption that the acceleration in the y direction had to be 0. It might move sideways, but it would not move up and down. Other problems, there'll be other tricks that you'll have to employ. And so most of what we're going to be doing for the next 3 chapters, actually, is just learning what tricks to employ when I use that process. So far, so good. You guys with me on this?
A little, yeah.
It's going to take a little bit of practice. So let's try something different. Now, it's early yet, and you may not have picked up on this, but I am a tremendous nerd. Gigantic nerd. And as such, I am an expert on all things comic book. And so if you don't already know this, let me, get you informed. The best superhero in existence, the absolute pinnacle of superheroism, is the Amazing Spider-Man. I will accept no other answers. There is no other answer. If you say Batman, you are dead to me. Spider-Man is the best superhero. This is a stone cold fact. Now, if you read Spider-Man comics, one of the things that Spidey loves to do when he catches bad guys is he'll go to the police station and he'll web them up to lampposts and just leave them for somebody else to find because he's already defeated them. He's done his job and he's got to get out of there because cops are jerks and they'll arrest Spider-Man too. So let's say that Spider-Man has caught a criminal and he's strung him up outside of the police station. And so here is the poor hapless criminal. And he is strung up using webs. And one of these webs is shooting off and it's attaching to a light post over here. The other web is shooting off at a slightly shallower angle because it's hitting a light post that's a little bit further away. Let's say this angle over here is 45 degrees, but this angle over here is a little shallower, 30 degrees. And this guy is hanging in midair. Make those poles a little tighter so he's not touching the ground. And what I want to do is I want to figure out how hard each of these webs has to pull to keep that criminal from falling to the ground. Well, this is a Newton's law problem. And in order to solve this Newton's law problem, I'm going to go through those same 4 steps we were just talking about. Step 1 is I'm going to draw a diagram, specifically a free body diagram, where I identify all of the forces that are acting on my object of interest. Now, the object of interest in this particular problem is this bad guy, right? This bad guy has several forces acting on him. I need to know what they are. So, what are the forces that are acting on that bad guy?
Gravity.
Yeah, obviously gravity pulls the bad guy downward. It's going to be his weight, which is equal to his mass times g. And let's say that this bad guy, let's give him a mass of 100 kilograms, right? That's about 220 pounds. So obviously that force is pulling him downward. That's one force acting on the bad guy. What other forces are acting on this bad guy?
Normal force.
So one of the things that people often get in trouble for is we come, as we start to learn names of forces and they're identifying forces, they just kind of go through the list of names in their heads. And so sometimes they'll apply the normal force when it doesn't apply. And this is one of those cases. So the normal force is a force of contact between your object and something else.
Okay.
So if there's a normal force in this problem, what would be the pusher?
Would the ceiling be the pushers or the web, since he's like pinning them up to the ceiling
Well,
to capture them?
yeah, he's definitely, the bad guy's definitely touching the webs, right?
Right.
So the webs will definitely exert a force. We'll learn a name for this force later, but let's avoid names for a bit. I'm just going to call this W for web. Right. So I'll have W1 and W2. Oh God, it's my taxes. Ha 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 ha. Come for the physics, stay for the bad jokes. But in terms of the normal force, like if he was touching the ground, there'd be a force from the ground pushing him up. But he's hanging above the ground, so there's no force there. And if he was actually touching the ceiling of something, there'd be a force from the ceiling. The ceiling would have to push you downward. But this guy's not actually hanging, like he's not attached to the ceiling. He's kind of like strung, and the webs are touching the flagpoles, but he's not. He's hanging in midair. So there's no force from the ceiling either. And one thing that might confuse you is, remember, we're only worried about the forces being felt by the bad guy. Now, like if the web is pulling the bad guy up and to the right, that means the web is also pushing the pole down and to the left. But we don't care about the pole. We assume that the pole has enough forces on it to keep it from moving. And we're concerned mostly about the bad guy not moving. So I'm not going to do another free body diagram for the pole. I could if I wanted to, but it won't be important for this problem. So in this case, the only things touching the bad guy are the 2 webs. So I've got forces from both of those, and then I've got the force from gravity, and that's it. You guys with me on that?
Yeah.
So that's step 1. I've identified my forces, and apparently I have 3 of them. Now, for each of those 3 forces, I need to break them down into their X and Y components. So first, let's do gravity. Normally, I would call gravity W, but I use W for the web, so I'm just going to write out the word gravity. But gravity is going to have an I hat and a J hat component. What are the I hat and J hat components for gravity?
Is it the 30 and the 45?
Nope.
No.
The mass and the gravity, 9.8.
Yeah, I mean, the force, the amount, the magnitude of the force of gravity is m times g, and his m is 100. But what direction is it? It points straight down. So when I'm doing components, I have to choose a coordinate system, and I'm going to keep a regular boring coordinate system where x is positive going to the right, but y is positive going up. But if that's the case, since gravity is down, it's going to be in the negative y direction. But it's not sideways at all, so it won't be anything in the x direction. So it'll be 0 for the x direction, 0 I hat, minus mg j hat. Everybody on board for that? We cool with that?
Yes.
So now I've got that. So now what's going to happen is I'm going to split web number 1 into components. So W1, but what's going to happen is W1 is a little bit diagonal. It pulls a little bit to the right, but also a little bit upward. And so whatever force it's pulling with, it's being split 2 different ways. And again, what I'll do is SOHCAHTOA, and that's where that 45 degrees is going to come in. Because if web 1, I'm going to draw it again down here, makes a 45-degree angle, here's the x part, it's to the right, here's the y part, it's up. Now I can do SOHCAHTOA. And I know that, for instance, the cosine of 45 degrees has to equal the adjacent side of the triangle. And again, if you're having a hard time identifying which ones are opposite, which ones are adjacent, the general rule is this, right? Right, here's the right angle, and the hypotenuse is always across from the right angle. So W1, the total force, is my hypotenuse. The adjacent side is the side of the triangle that touches the angle, but isn't the hypotenuse. So you can see this touches that angle, this touches that angle. So the x part is the adjacent side of the triangle. And the opposite side of the triangle does not touch the angle at all. It's over here, it doesn't touch that 45-degree angle. So the cosine of 45 is adjacent over hypotenuse. So x over the total web force, which we don't yet know. I'm going to solve this for the x part by getting this on the other side. So the x component is going to be whatever the total force is times the cosine of 45. That's the I hat part. And this same trick with the sine will get me the j hat part, because the sine of 45 is opposite over hypotenuse. However, never mind. So there's the components of web 1. I've got its x part and its y part. I don't know how big W1 is. I'll have to solve for that letter later, but for the time being, I'm just going to leave a variable in place as a placeholder for a number I haven't figured out yet. Now, for W2, I'll do the same trick. And it'll work pretty much the exact same way, except that its x part is to the left, its y part is upward, and it makes a shallower angle. Now, because the x part is to the left, I'm going to slap a minus sign on it to reflect the fact that it's to the left, because I said right is positive, therefore left is negative. And this will be W2 times the cosine of 30 degrees. But because the y part is still upward, I'll leave that as positive. And I'll break that into components. So just like the previous problem, I have broken everything up into its x and y components. And step 3 is I'm going to find equations. And I'm going to find those equations by using Newton's second law. The sum of all the forces has to equal m times the acceleration. But I got to do that one component at a time. So I'm going to end up with two equations, one in the x direction, another in the y direction. In the x direction, I have more than one force this time because I have this plus this plus this. So 0, then I got to write it, plus this, so W1 cosine of 45, minus, because it's plus a negative, so minus W2 cosine of 30. That has to equal the mass of the bad guy times the acceleration of the bad guy in the x direction. Neat. That's one equation. Could I solve it? Not yet, because I don't know W1, I don't know W2. There's two unknowns in that equation. So we'll leave this, figure it out in a minute.
Question.
Yes.
Can you repeat that one more time? I'm kind of lost.
Okay. Yeah. So what we're doing is we're doing Newton's second law, right? Newton's second law says the sum of the forces equals m times a, right? But the sum of the forces and a, they're both vectors. And when you add vectors, you do them one component at a time. So I'm first going to do the x component. That's all the I hat stuff. So to do the sum of the forces, I'm adding up all the forces in the x direction. So I added all that and got this. That's the sum of the forces.
Okay.
That had to equal ma, but since we're only talking about the x direction, it's only the part of the acceleration that's in the sideways direction.
Okay.
That's why I call it a sub x.
Okay, got it.
Yeah. Now, in the y direction, we'll do the same deal, except now I'm going to use all these guys. So I have this plus this. I'm going to write the positive ones first so I can do the negative one last. It looks prettier. So I'll have W1 times the sine of 45 plus W2 times the sine of 30 minus the force of gravity, mg. That's going to equal m times the acceleration in the y direction. So once I get here in finding my equations, I always like to pause and I want to ask myself, do I know anything at all from the nature of this problem about the acceleration that I'm going to get? Like in the previous problem we just did, we figured out from common sense that the box wasn't going to sink into the ground. So it couldn't have an acceleration that was negative in the y direction. And so we set that acceleration equal to 0 in the previous problem. For this problem, what do I know about the acceleration of the bad guy after Spidey hangs him up outside the police station? What acceleration is this bad guy going to have?
0, because he doesn't move?
Yeah, the whole point is he's not going anywhere, right? Spider-Man has tied him up. If he can't be moving, he certainly cannot be accelerating, which means this guy is not moving in the sideways direction or up and down. This is what we call a static equilibrium problem. Static equilibrium problem simply means that your object is stationary, static. Equilibrium means balance, right? Because what's happening is in order for him to remain stationary, these three forces have to balance out and cancel. So the acceleration in both cases has to be 0. All the forces in the x direction have to add up to 0. All the forces in the y direction also have to add up to 0. So there are my two equations. And now that I've gotten rid of the acceleration, everything in these equations is known except for W1 and W2. So I have two equations and two unknowns. That is a solvable problem. I keep hitting the table and putting my thing out of focus. This is crazy. All right, so how do I solve this? At this point, it's a math problem and not a physics problem. All the physics happened in all these steps. Now we just got to do the math to solve for W1 and W2. If this was an exam problem, just so you know, this is the 14 out of 20 points mark, because the last 6 points is just, can you do algebra? So I want to solve for W1 and W2. But what's making this a little bit complicated for me is that in this first equation, both of my unknowns appear in that equation, which means I can't solve it. In this equation, both of my unknowns appear in that equation. Can't solve that either. So I'm going to have to solve these two equations simultaneously, which is a trick that you guys learned way back in algebra in junior high or high school, wherever you took algebra for the first time. And the trick for solving this is to pick one of your equations, and it doesn't matter which one you pick, although your life might be a little easier if you pick the one that looks simpler, which there's less going on in that first one. So I'm going to start with that first one. So pick one of your equations, and then pick one of your unknowns and get that unknown by itself. So what I'm going to do is I'm going to take this first equation, and I'm going to get W1 by itself. So get W1 on one side, everything else on the other side. So if I take this, the easiest way to do that is to take this negative thing and add it to both sides. So what I'll end up with is on the left-hand side, W1 times the cosine of 45 is going to have to equal W2 times the cosine of 30. So far, so good. Then I can get this cosine of 45 out of here by dividing both sides by the cosine of 45.
I have a question.
Uh-huh.
What about the mass?
So what's going to happen is the mass appeared on the right-hand side where you had MA, right?
Yes, yeah.
So if I have 100 kilograms times 0, that's still 0.
Oh, got it. Yeah.
So the mass ended up not mattering for this problem yet, at least over here, because we were multiplying it by 0. Now notice the mass still matters because it still appears here.
Okay.
So by the time we're done, this mass will be important, but it hasn't been important yet.
Okay.
So W1 equals all this. I don't have a number for W2 yet, so I can't solve that. But if I take this expression for W1 and I plug that into the other equation, the one that I haven't used yet, well, once I replace W1 with all of this, W1 will no longer appear in that equation, and the only variable will be W2. So let's do that. Let's take this equation. I'm replacing W1 with this. So I've got W2 cosine of 30 over the cosine of 45. So that's what used to be W1 times the sine of 45, because that was what was times W1 to begin with, plus W2 again times the sine of 30 minus gravity equals 0. So that's that other equation. I've just replaced W1 with what W1 equaled. And it seems like it might be a little bit complicated, but it's really not. Let's simplify things down. So the first thing I notice is that this first term has W2 in it. This term has W2 in it. This term over here doesn't have W2 in it. Let's get everything that doesn't have a W2 on one side, everything that does have a W2 on the other side. So let's just add this to both sides. So now I've got W2 cosine 30 times the sine of 45 over the cosine of 45 plus W2 sine of 30 equals the weight of the bad guy. And again, this seems kind of ugly and complicated. It's really not. Because remember, cosine 30 is a number. Sine 45 is a number. Cosine 45 is a number. So what I have is a number times W2 plus a different number times W2. Well, if this was algebra, you had like 3x plus 2x. You know that's 5x, right? How did you get that? You factor the W2 out. And therefore, W2 is going to equal mg divided by all this garbage. And that is stuff that I can plug numbers in for. That's 100. That's 9.8. The sine of 5 over the cosine of 45 is the tangent of 45, which just happens to be 1. So it's 1 times the cosine of 30. Cosine of 30 is square root of 3 over 2, which is 0.866. The sine of 30 is a half, so plus 0.5. So this entire thing is 1.366. So it's 980 divided by 1.366. I get that W2, the force exerted by the web on the left, is 717 newtons. We'll call it 0.4. Let's go. Yay! So now I know how hard that web has to pull. What about web 1? Well, along the way, we'd already solved for web 1, right? Web 1 was just web 2 times the cosine of 30 divided by the cosine of 45. So let's plug that 717 into here. Times cosine of 30 divided by...
When you're done, can you go back, please?
Yeah, absolutely. So that's the force being exerted by the second one. So again, what did we do? We set up the equation for W2, got W2 by itself. We plugged in all our numbers, got a number for W2, and then took that answer, plugged it back in for W1, and now we're finished. Super easy. So far, so good. You guys feel okay with this?
Not exactly, but I know I have to practice a lot.
Yeah, I mean, there's no way around it. You're going to have to do some practice. The tricky part is just, when in doubt, remember the same 4 steps every time. Make sure you go back to fundamentals. If you're ever stumped on a problem, go back to the fundamentals, and usually you'll be able to figure your way out of it. And again, all we're going to be doing for the next couple of chapters is we'll be learning some tricks that you'll use in different situations, things to be on the lookout for, right? This first one here was a static equilibrium problem. So what was the thing I was looking out for? I was looking out for the fact that the object that I was dealing with, I knew it wasn't moving, right? The problem told me that the guy was just hung up in the air, not going anywhere. And if that's the case, he could not have been accelerating. So when I got to the part where I was doing F equals ma, I was able to set all the accelerations to be 0. And that allowed me to solve the problem. Make it more complicated. So this next little bit is one of those bread and butter kinds of physics problems. I can guarantee you that on your second exam, where we do Newton's laws, there will be a problem on it not unlike this in some way. On your final exam, I guarantee you there will be a problem not unlike this in some way. It's a thing on a ramp. Physicists love putting things on ramps. We love it. It's every physics test ever made by any professor at any school probably has at some point some kind of thing sliding on some kind of incline. It's just a classic problem that you can't avoid if you're taking this class. So let's imagine that I have the following scenario, right? Here's a...
Since we are in a subject in terms of taste, what is our first taste?
Your first test is going to, we talked about this the other day, your first test is going to go live sometime Thursday, and will be due Friday night at midnight. I'll leave it open for about 20 or between 24 and 48 hours.
Okay.
The exam will be a 2-hour exam, so find a 2-hour block where you can do this uninterrupted. But you can start at any time during that time.
So we have to record what we're doing, or how is that?
Well, what will happen, and I'll post the tech test for this hopefully this afternoon.
Okay.
But you'll have to install the lockdown browser, and you'll have to use the respondus monitor where like the Big Brother cam will watch you while you take your exam. It'll lock down your browser so you can't have other browser windows open. It'll be watching you so that you can't be like having on another device or something, so you can't pull your phone out or something without getting flagged. It'll be open notes. If you want to have your notes, by all means, use them. I'm cool with that.
Okay.
But once you start it, you'll have 2 hours to do it. It'll shut you down in 2 hours.
Okay.
At the end of that 2 hours, what you will then do is within the next 10 to 15 minutes, you'll upload your work. Right? It's got to be pretty quick. If it's not within the next 10 minutes or so, you need to let me know what's going on, because I can't have you cheating during that unmonitored time.
Okay.
Make sense?
Yes, and then the other stuff. Are you gonna give us like practice days that we can study, prepare for the exam?
Well, I don't give you practice tests, but what I do give you is homeworks. If you're prepping for your exam, the homeworks are kind of the practice test. That's the kind of stuff that I'm going to put on your exam. But I generally am not a fan of giving you a test and then giving you another test where I just basically scratch all the numbers off and replace them with new numbers. That's not a very good test of how well you know the physics.
Okay.
Yeah.
Thank you.
All right. So, box on a ramp. Here's a ramp. Here's a box. And what's going to happen is I want to push this box up the ramp. So I'm going to push with 100 newtons of force. Parallel to the ramp. All right. Let's say this box has a mass of, let's say, 5 kilograms. And the ramp itself is slippery. Right? What's the acceleration of the box? So, the same 4 steps we do for every Newton's law problem ever. All that's going to change is that when we implement one of the steps, there's going to be a little trick that we're going to do because we have a box on a ramp, and then we're off to the races. So, step 1, we need to identify what our forces are. So, what forces are acting on this box?
Gravity.
Yeah. Now, gravity does not care that you're on a ramp. Gravity always pulls you straight down. So gravity is the mass of the box, which we know, times g. What else we got?
It's moving, right?
Hopefully.
Normal force.
Yeah. It's touching the ramp, so there'll be a normal force from the ramp. Now, what direction is that force going to be?
Parallel to the ramp.
Not parallel to the ramp, perpendicular.
Perpendicular, yeah.
Yeah. Yeah. So perpendicular to the ramp is not straight up, but it'll be diagonally up. Excuse me, like that.
Sure.
Thank you. All right, what other forces are acting on this box?
The opposite force, the one we push in and right, they have to be the other direction.
Yeah. I'm applying a force, like I'm pushing the box, right?
Yeah.
And it says that I'm trying to push the box up the ramp. So it's parallel to the ramp. It's going to be not straight up or not straight sideways, but parallel to the ramp is what it says in the problem. I'm going to call it P for push. And it's 100 newtons. Now, just a real quick caveat. there's a problem on your homework that's almost exactly the same as this. However, this is not the same problem. Read carefully. It's different. The thing that's different is that in this example, I'm pushing parallel to the ramp. I'm pushing diagonally up the ramp. But on the problem that's on homework, you're pushing horizontally. You're pushing straight sideways. So this problem will look different when you do that problem on your homework, and I'll let you guys figure that out. That is an exercise left to the reader. Now, are there any other forces acting on this box?
Since it's slippery, there is no friction force.
Yep, there's no friction. Don't have to worry about that. Is there anything else touching the box?
Yes, the person who pushed it.
Oh, but we already got that.
Okay. What about the RAM? Whatever it's ground force. Is it ground? Yeah.
What that's this, right? This is the force from the ground. So we got the ground, we got the person, we got gravity. Nothing else is touching that box. We're good to go. There's only 3 forces in this problem.
Okay.
So step 2, we're going to choose a coordinate system, and we're going to break those forces up into that coordinate system. And this is where the trick is going to come in. This is the part that's tricky. Because technically, you can pick any coordinate system you want. If you want up to be the x direction and sideways to be the y direction, whatever. Do you. If you want to the right to be positive and the left to be negative, that's cool. But if you'd rather have left be negative and right be positive, that's also cool. As long as you're consistent, you can pick whatever coordinate system you want, and you'll always get the right answer. It doesn't matter. It's just that sometimes some coordinate systems make your life easier than others. And so when you choose your coordinate system, you got to make sure you know what you've just picked. And there are certain choices of coordinate system that will make this problem be easier than others. Specifically, if I were to go and choose like a regular traditional coordinate system where x is to the right and y is straight up and down, then what's going to happen is when I go to break these forces down, what's going to happen is gravity is going to be purely in the y direction, but not the x. It points straight down, but not sideways. So this would have a 0x part and a negative y part. Now, the normal force would be diagonal. It would be a little bit in the positive x direction because it points a little bit to the right, but also a little bit in the positive y direction because it points a little bit up. The push would be a little bit in the negative x direction, but a little bit in the positive y direction. So I could split all 3 of those things up into components. That's no big deal. But when it comes to the acceleration, what's going to happen is I know what this box is going to do, right? If I push this box like that, how is that box going to move?
Upward?
Yeah, it's going to slide up the ramp, right? If it moves, it's moving this direction, which means it's moving diagonally. It would have a little acceleration sideways and another little acceleration up and down. So the x component and the y component of the acceleration would both be non-zero, and I would have to solve for both components. That stinks. That's me having to solve for 2 things, and that might make it more difficult for me. It's not impossible. I could still do it because I'd get 2 equations, one from the x direction and one from the y direction. So I'd have 2 equations and 2 unknowns. So I could probably still solve the problem maybe, but it would be hard. Actually, now that I think about it, I wouldn't be able to solve it at all. It'd be too complicated. But either way, it would suck. I don't want to do it. However, there's no rule that says when I choose my coordinate system that I have to choose this coordinate system. There's no rule that says x has to be sideways and y has to be up and down. I can pick whatever the heck I want. So here's what I'm going to do. I'm going to be clever when I choose my coordinate system. Because look, I know this box is going to move straight up the ramp. So what I'm going to do is I'm going to take a coordinate system and I'm going to pick a coordinate system that is slanty, just like the ramp is. So I'm going to have my x direction be straight up the ramp. I'm going to call that the positive x direction. There's no rule that says I can't do that. So I'm going to do it. Now, if that's the positive x direction, the one rule that I do have is that y has to be perpendicular to x. So if y points straight up the ramp, then or if x points straight up the ramp, y has to point perpendicular to the ramp. So all I've done is I've taken my regular coordinate system and I've slanted it. So it's up the ramp and perpendicular to the ramp. That's it. Now, here's why that helps me. Here's why that's going to make my life easier. All right. When I go to break my forces into components, some of the components that used to be diagonal compared to my coordinate system, like the normal force, they're not diagonal anymore. Now, this normal force points the same direction as the y-axis. So the normal force is going to have a y component but no x component. This push force would have been slanty in a regular coordinate system, but here it's only in the x direction, not at all in the y direction. Gravity used to be only in the y direction. Now it's going to be a little bit in the y direction and a little bit in the x direction. So gravity is going to have to get split into components. That's harder than it used to be, but that's a trade-off. But more importantly, when it comes to my acceleration, I get a ton of mileage out of this choice. Because what's going to happen is the acceleration in the x direction might be not zero. It could be accelerating up the ramp. But the box is not going to move this direction at all, right? It's going to move in the x direction for sure, but it will not be moving in the y direction, because that would mean it either flies off the ramp, which it's not going to do, or sinks into the ramp, which it's not going to do. So by choosing that coordinate system, I automatically know that the y component of the acceleration has to be zero. That means there's one less acceleration for me to solve for. It's going to be way, way easier to do this problem. So that's the trick. For a box on a ramp problem, when you're choosing your coordinate system, you don't just choose any coordinate system. Choose a coordinate system that is slanty, just like the ramp is, and it will make the problem easier. Awesome. So with that in mind, let's break my forces into their components. Right? What are the components of P? Well, P is only in the x direction, but it's not in the y direction. So it's whatever the push is, 100 newtons, so I'm going to call that P, I hat, but it's 0 J hat. For the normal force, it's purely in the y direction. It's not in the x direction at all. So 0 for whatever I hat is, and then whatever the normal force is for J hat. The tricky part is the gravity, the weight. And to do this one, here's what's going to happen. Let's say that this ramp makes a 30-degree angle with the horizontal. That's the angle of my ramp. Now, what's going to happen is, because my ramp is slanty, gravity is going to make a certain angle with my y-axis. And it turns out that this angle right here will always be the same as this angle right there. If you can't see that easily, the way that I can track it myself, the way that I kind of make it make sense, is, let me switch off the share for a second. So look, imagine this is my ramp, right? My ramp is slanty. And imagine that this is the force of gravity. Gravity is always going to point straight down, right? And what's going to happen, let's go back so you can see that. What's going to happen is I'm choosing my y-axis to always be perpendicular to my ramp. So here is my y-axis that's always perpendicular to my ramp. And you'll notice that as it is now, I need more fingers. As it is now, here's my ramp, here's the y-axis, here's gravity. There's an angle being made between those two things that's non-zero. But what if the ramp weren't a ramp? What if the ramp was flat, like just level ground? If the ground is level, then my y-axis would be perpendicular to that. It would point straight up and down. And gravity would point straight up and down. So the angle between them, if the ground was flat, would be 0. Well, that means that if the ramp was flat, the angle of the ramp would be not 30 degrees, but 0 degrees. So when the angle of the ramp is 0, the angle between gravity and the perpendicular are also 0. But what about if I make the ramp super, super steep? What if I crank this up all the way to 90 degrees? So this angle is 90 degrees. If I do that, the y-axis would point perpendicular to the ramp. It'd be sideways. And the angle between sideways and gravity would have been 90 degrees. So the thing that I can kind of convince myself when I think it through that way is that when the angle of the ramp is 0, the angle between the y-axis and gravity is 0. When the angle is 90, the angle between the y-axis and gravity is 90. So clearly, those two angles are the same. And even in between, they still have to be the same. So if that explanation doesn't make sense to you, and it's harder for me to illustrate because I don't have the same number of visual aids that I have normally in a regular classroom, if you don't buy that, you just got to memorize it. You know that this angle right here has got to be the same as that angle right there.
But how do you get 30 degree?
In the problem, we're going to specify what the angle of the ramp is.
All right.
So in this case, the ramp makes a 30-degree angle, and we're going to use that to solve the rest of the problem.
Okay.
So having said that, here's the x component of gravity. Here's the y component of gravity. And you can see I have a little right triangle. There's my right angle. I'm going to redraw it off to the side so it's easier to see. So here's gravity pointing straight down. Here's the y part of gravity pointing into the ramp, so it's negative. Here's the y part of gravity, or the x part of gravity, pointing parallel to the ramp. That's a right angle. This right here is 30 degrees. This right here is the hypotenuse equal to mg. And once I see that triangle, now I can do SOHCAHTOA to figure out the parts. Notice the x part is the opposite side of the triangle. So if I do sine of 30, that's the x part over mg, which means the x part will equal mg sine 30. That's unusual because 9 times out of 10, the x part of something is going to come from the cosine. This is one of the situations where the x part does not come from the cosine. It comes from the sine. Come on, autofocus. There you go. That's still crappy, whatever. So this is the x part, and up the ramp is positive, down the ramp is negative. It's definitely pulling it down the ramp, so it's negative mg sine 30 I hat. The y component I'm going to get from the adjacent side of the triangle. It's still negative because positive y points out of the ramp, but gravity is trying to pull it into the ramp. So minus mg cosine 30 j hat. And so those are the components of the weight when I break them down. So that's the trick to this problem. That's the thing that makes this problem a little different from other problems, is that in order to do this effectively, we're going to slant our coordinate system and break our coordinates up that way rather than a more traditional way. Now it's all over but the crying, because I got to find my equations, which means do the sum of the forces equals ma. And in the x direction, I have the sum of the forces is this plus this plus this. So I'm going to have P minus mg sine of 30. That's going to equal m times the acceleration in the x direction. That's one equation. The second equation is going to be in the y direction, where I have this plus this plus this. So n minus mg cosine of 30 is going to equal m times the acceleration in the y direction. And every time you get to this point in a problem, you always want to pause and ask yourself, do I know anything at all about the acceleration in this problem? And the answer is here I do. Here I know it's going to move in the x direction, but it won't be moving in the y direction. So while the x component might not be 0, the y component must be 0. So there's only one acceleration to solve for, and that's this. And oh, look, I know m, I know g, I know p. Everything in that equation is known. Just solve for a. Piece of cake. So I plug in. That's 100, we said. M was 5. So 100 minus 49 times sine of 30 divided by 5. And I get 15.1. And that's the acceleration of that box. So the process is the same for every one of these problems. You're always doing the same kinds of steps. All that we're ever doing is implementing a different trick to deal with certain situations. And we'll learn several more during the rest of this week. All right, hopefully this made sense to you guys and you have a good sense of stuff. If you haven't already, you should definitely take a crack at the Chapter 4 homeworks. The Chapter 4 homework set is pretty short because what happens is Chapter 4 introduces Newton's laws in its base form, and then Chapter 5 introduces several more of the additional tricks that you'll use with particular forces like friction. And so the meat of the problem is Chapter 5, but Chapter 4 and 5 are very, very similar with the exception of there's just a couple extra tricks you learn in Chapter 5. So I would take a crack at Chapters 4 and 5 for that matter. They should be pretty doable. I think the due date that's currently set for them is earlier than it will be. I'm going to push that back. I just haven't gotten around to going through Canvas because it takes forever. I have to go one problem at a time. So that's coming up. So don't freak out about the due date. It's not as early as it seems. I think it says like Thursday, but I'd probably push it to like early next week. So if you've got time, take a crack at them, but don't feel like you have to rush. Any other questions you guys have?
No, but can I see you in your office hours?
You certainly can. You know how to find me.
Thank you.
You're welcome, guys. All right. I'm leaving it at that. Have a good day.
You too.